Hello everybody, my name is Rebecca Phillipps and I'm a senior lecturer in anthropology at the University of Auckland. I'm going to be presenting our paper today on the application of machine learning to stone artefact identification together with my colleagues Josh Emmitt and Sina Masoud-Ansari. Stone artefacts are ubiquitous in archaeological contexts worldwide, including in Aotearoa, New Zealand. The analysis of stone artefacts are used to draw conclusions about human behaviour, and approaches have developed significantly throughout the 20th and 21st centuries. Most studies of assemblages from pre-European Māori contexts tend to focus on geological sourcing. However, these studies have limited value if the composition of assemblages, including taphonomic processes like fragmentation, are not also understood. Large quantities of stone artefacts collected through academic research and commercial heritage practice often go unanalyzed and remain in storage in museums, labs, and other such facilities. This means potential knowledge is not available to those working in the heritage sector and wider communities. This is largely an issue to do with capacity. Very few archaeologists in New Zealand are able to analyze stone artefacts in detail. This is not a problem that will go away, as increased impetus on housing and infrastructure development and processes like coastal erosion necessitates mitigation on a very large scale. Given the weight of legacy collections, the present crisis of accumulation, and lack of expertise in the field, we are working on developing methods to rapidly analyze stone artefacts. We use stone artefacts from 3 different locations to train and test the model. This includes artefacts from Australia, Egypt, and New Zealand. While the intent of the project is to focus on stone artefacts from New Zealand, the access to legacy data from previous projects we have been involved in afforded us the opportunity to bolster our sample with minimal time cost. The Western New South Wales Archaeological Program, otherwise known as WinSWAP, involved a geological approach to the interpretation of extensive surface artefact scatters in the semi-arid landscape. Surface scatters of flake stone artefacts, the majority manufactured from quartz and silkrete, are scattered across eroded surfaces adjacent to creek lines. Over a dozen years, WinSWAP researchers mapped the location and recorded attributes from tens of thousands of these artefacts. This project is unique in that, at the request of elders of the Barkindji people, the traditional owners of the area, no artefacts were removed from country. Every artefact was analysed in the field and put back in place. Of relevance here is one aspect of the research program involving the implementation of a quality assurance study to assess inter-observer variability. This program involved the reanalysis of a sample of artefacts by one observer in comparison of the attributes recorded and measurements taken from those obtained by a number of other observers. The study assessed systematic and random errors introduced by multiple observers, and as part of the study, photographs were taken of the artefacts selected for repeat recording. The photographs and associated attributes and measurements form the data analysed here. These data come from 3 WinSWAP projects: Stud Creek area, Fowler's Gap area, and Rutherford's Creek. Data collection occurred during the 1990s and into the early 2000s. Stone artefact attributes and measurements recorded follow definitions described in Holdaway and Stern 2004. The Fayum project is a collaboration between the University of California, Los Angeles, the Rijksuniversiteit Groningen, and the University of Auckland. A large-scale surface survey was undertaken between 2008 and 2012. During this fieldwork, a methodology was applied similar to that of WinSWAP, in that surface scatters of flake stone artefacts, almost exclusively flint, cover the northern shoreline of Lake Karun in the Fayum. The location of these objects were recorded in addition to attributes of thousands of artefacts. The study also included a geoarchaeological component to understand processes of landscape formation and excavation of buried features to procure radiocarbon samples. As with the WinSWAP study, a quality assurance protocol was implemented that included photographing each artefact selected for repeat recording. All stone artefact attributes and measurements follow definitions in Holdaway and Stern, supplemented by information related to local North African tool typology found in a variety of publications. The Ahuahu Great Mercury Island project is a collaboration between the University of Auckland, Auckland Museum, landowners, and tangata whenua Ngāti Hei ki Wharekaho, the tribe who have ancestral connection and authority. The project has carried out a survey and excavation on Ahuahu since 2012. The majority of stone artefacts discovered on this project are from excavated context and were brought back to the lab at the University of Auckland for further analysis. A variety of studies have been undertaken to geochemically source and describe the attributes of these artefacts, largely manufactured in obsidian, basalt, and chert. Artefacts were also photographed for the purposes of this study, and all stone artefact attributes and measurements follow definitions from Holdaway and Stern 2004. The identification of stone artefacts produced by humans are commonly distinguished from natural lithic clasts. Conventionally, this relies on the ability of observers to identify landmark features such as flake scars. Consistent identification requires skill, and even if basic knowledge is acquired, identification may be difficult due to raw material type or the fragmentation of the object. But most practitioners, even the most inexperienced, are able to record some metric information, but the ability to also classify artifacts by class, such as flake, core, or tool, can provide good information on assemblage composition. This may then be used to interpret aspects of human behavior ranging from raw material procurement, manufacture, object use, discard, and post-depositional processes. Even at a most basic level, in a commercial heritage setting, stone artifacts indicate the presence of archaeological remains. Therefore, rapid identification of stone artifacts as distinct from natural lithic class is desirable. Machine learning offers one solution. Current applications seek to classify artifacts or landscape features. Here we apply machine learning in the context of flake stone artifact identification, seeking firstly to differentiate natural class from flake stone artifacts, and secondly to differentiate flakes, cores, and tools. This is composed of two tiers. Tier 1 is to differentiate rocks from stone artifacts. A range of different rock shapes and raw materials were used to mimic the sorts of natural class that may be encountered in the field. Tier 2 aims to differentiate rocks in three common stone artifact classes: flakes, cores, and tools. One of the challenges in the training stage is the composition of archaeological assemblages. Due to the nature of lithic manufacture, flakes are almost always more common by far than cores and tools. This requires sampling and augmentation of the data, which we will discuss below.
My name's Sina, and I'll be talking about data generation, pre-processing, and the application of machine learning. Training data was generated using the open source Python program Annotate to Kitty. In total, approximately 5,000 images were annotated by manually marking a bounding box around each object. The object bounds and classification label were stored in Kitty format. The Kitty format supports multiple objects with varying class labels per image and is one of several standard annotation formats used in object detection. During our initial exploration in applying machine learning to image classification, we attempted to improve accuracy by cropping artifacts from their respective backgrounds. Since we could not develop a consistent approach using traditional computer vision methods such as boundary detection, especially against complex backgrounds, we opted instead to develop a training dataset that would support a combined object detection and classification approach. By using machine learning to solve the object detection problem, we further automate the task of classification and expand its scope to multiple objects with the ability to support robust identification across a variety of image backgrounds. The second step in preparing data for machine learning was to standardize image resolutions. All images and their respective bounding boxes were resized to 300 by 300 pixels using the CV data package, an open source library for manipulating computer vision datasets. This package was not found to respect EXIF rotation metadata, so additional software was written to rotate all images where needed, prior to resizing. We opted to maintain image aspect ratios during resizing, padding with black pixels where necessary. An object detection workflow was developed using a publicly available PyTorch implementation of faster RCNN ResNet 50, a neural network model that learns to propose and then classify regions of interest. Raw image data consisting of RGB pixel values are processed through convolutional network layers, which learn a hierarchy of image features. At the most simple level, these features consist of changes in color gradient, which are combined into higher level features such as edges. In turn, the model can learn to identify arrangements of such features that are indicative of the fracture planes that can be used to distinguish between rocks and artifacts, as well as specific types of stone artifacts. The object detection module in faster RCNN also uses a convolutional network to propose regions, and with each region being assigned an objectness score. These region proposals are then fed into a classification module, which assigns a class label. The example on the right shows the output from a trained model in which 3 regions are proposed, each with a different classification. The values represent the likely presence of a class label and range from 0 to 1. The ground truth bounding box is shown in red, with each of the object proposals in green. In this case, the proposal with the highest classification score is tool, which matches the ground truth. Model training was performed on an NVIDIA V100 GPU using the Adam optimizer with a learning rate of 0.01, gradient clipping of 1, and batch size of 32. Images were augmented during training using randomized horizontal flipping with probability of 0.5. For Tier 1, training was performed using k-fold cross-validation. Cross-validation helps to remove bias from random partitioning between data used for training and data used to test the model. We divide all training samples into 5 partitions, using 4 for training and the remainder for testing. The partition selected for testing is rotated so that all partitions are eventually used for both training and testing a model. For Tier 2, due to the limited number of samples for cores and tools, 5 balanced data partitions were created by selecting all cores and tools and then randomly sampling 300 flakes and 300 rocks. Each of the resulting partitions were randomly sorted into training and test sets, with 20% of samples reserved for the test set. The results presented are the average across the 5 data partitions for each tier. We consider top 1 accuracy, which is whether the highest scored proposal matches the ground truth. The values are average percentage accuracy scores. Tier 1 results suggest the model is very capable of distinguishing between rocks and stone artifacts, with a cross-validated mean accuracy of 100% over test partitions of 160 sample images. Tier 2 results continue to show strong performance in predicting rocks, with an average accuracy of 99.7% over test partitions of 238 images. Artifact classification has a top 1 accuracy of 70.2%, with the confusion matrix showing weak classification performance on cores and moderate performance on flakes and tools. Total training time to generate average results was approximately 5 hours for each tier.
Hi, this is Josh Emmitt. I'll take over for the last part of this talk. So the initial results from the study suggest that a high degree of confidence can be achieved in identifying an artifact versus a natural lithic clast, as well as moderate success identifying basic categories of flakes, cores, and tools. Potential applications of this technology include a variety of heritage contexts where specialist knowledge of stone artifacts is limited, as are funds for such projects. In addition, this project highlights problems with classification both from an ontological and methodological perspective. Classification of stone artifacts has a long history in archaeology and is often applied uncritically to analyses. Given the weight of human behavioral inference drawn from lithic classification, we suggest these issues warrant more detailed consideration, especially in locations like New Zealand where stone artifact studies are extremely limited. We plan to publish the results of this study as a benchmark for future development. However, we need to consider issues of data sovereignty and the variable data sovereignty aspirations of the communities we work with. Open data publishing models are not always appropriate, and archaeologists working in this space need to do more to ensure communities are involved and informed of the implications of publishing data such as benchmarks. This is not to say this is a roadblock, but more a discussion that needs to occur with communities. We are also looking to increase the variability of the classes considered, but this also needs the appropriate sample sizes. In this study for Tier 2, we sampled our largest classes to match the counts for the lower ones. Another option we plan to try is to augment the smaller samples to bolster the dataset size and potentially increase the accuracy. A larger sample of the smaller samples, cores and tools, would be more ideal. However, as discussed, due to the nature of the archaeological record, this may not be possible. A further level of analysis is comparing the results of the study with the human analysis of the photographs used. While the identification of the objects used in the study was carried out by archaeologists in the field and lab looking at actual objects they could hold, the algorithm is examining 2D images. We will analyze the photographs to identify them and then compare the results, with one possible conclusion being that 2D is not sufficient for the accurate identification of these objects. Further work also aims to integrate 3D models of artifacts, the aim of which is to train the classification of data closer to what archaeologists would do in the real world. Thank you.